complete before it comes back.
Right. When you're doing call, you're not starting a new process. You're just moving the program counter somewhere else.
Okay.
So I would say not even, I wouldn't even relate it to fork, wait, and exec, because wait is a parent process waiting for a child process. Exec is just like forgetting the previous process and replacing it with someone else. This is not quite what's happening in our program. We're still like in the same program. We're just calling like it's not a replacement routine or like an alternative routine. It's just like a subroutine. It's like a bro routine. It's just like jumping around. It's like it's still the same file, right? Like it's all inside the same file. It's just jumping around in different places, right? Like instead of it's a way of letting you instead of moving. I think I'll just set it this way. Instead of moving your program counter in a linear fashion, you can make it jump around, so you can access different spots at different times, however you want.
All right.
All right. Cool. All right, let's go through them one by one, and we'll have you guys answer. We'll take turns, so if you've answered one, just let someone else answer the next one. All right. What are some examples of instructions handled by the CPU as opposed to the ALU? Anyone?
LDI, print.
Yep. LDI, print, pop, push. Yeah, now that you've answered this, what operations are handled by the ALU?
Math operations like multiply.
Yep. Multiply.
Arithmetic
Also,
logic unit.
Yes. When you answer this tomorrow, make sure you include, so you said math, but also make sure you include comparisons, because that's going to get you 3 points, right? Like it's arithmetic and logic. So it's doing, where's the text? So it's not just doing A plus B. It's also doing is A greater than B, or
yeah. I suppose that falls into binary math. Yeah.
Yep.
Boolean math, not binary. Yeah.
Yep. All right. Okay. So I'm gonna keep track of who's been answering, so we don't have repeats. All right, so next up, someone else. Why are general purpose registers useful in assembly language?
It's like a variable. You can temporarily store a value and refer to it later.
Yep. What else can you store? What else do we store in registers?
I don't know. Let's see.
I mean, it's always variables, but there's like some specific ones we use our registers for.
Flags, maybe.
Addresses?
Flags, addresses. What's one specific flag we've been using? It's the first one we said.
Negative flag? I don't know.
The stack pointer?
Stack pointer?
Yep. Just one of the few things we can use the registers for. And then I think we haven't talked about this. Oh, no, yeah, actually we did. We sent you the pictures. What is the, Chad, what's the, why are registers so useful? How are they different from RAM or cache or a hard disk drive?
Well, they're closer to the CPU, so they're faster, but there's fewer of them.
All right, cool. All right, now this converts this 8-bit hex number to binary.
Can I take that one?
Let's have all of you. Cool. I think I interrupted you in the word. Let everyone try to do it by hand, just quickly, and show me the answer on the screen.
Huh?
So do it by hand and just like show me the answers on the camera. Let me do it.
How can you? What?
A piece of paper. Just write it down.
Oh. Uh,
I was wanting us to throw in gang signs.
And then do it in binary, and I want to see the process. Telling you this, by the way, because you being able to do it by hand is going to get you extra points in the questions tomorrow. All right, Elvis, can you put it closer? I'll just let you guys know if I see it. All right, so okay, wait just a second. Connor, Connor, no, you didn't get it right. Elvis, sorry, can you show me again?
Kind of hard to read, but it's the same one that Brian got.
Oh crap, Brian, I didn't see yours either. How do you?
He wrote it in the Slack channel.
Guys, don't give out the answers. Come on.
Oh, my bad. Oh man. So look.
Well, I'm glad that's the answer because that's the same one I got.
I don't have anything to write on my desk. What do you want about?
Do it in Paint or something, and then send me your answer. I'm on a DM. Come on,
The
you're the
same one Brian got, so.
that's cheating, guys. Come on.
Oh man, guys. I'm sorry, guys.
Send you my work. I didn't cheat.
hey, look at mine.
Steve's the gang sign.
I did the paper.
Wait. Give me a second. My mouse is stuck. I can't see anything. All right, let me see. All right, Elvis, you're just missing. Remember, nibbles have 4 digits, so your number is quite a bit smaller than it should be. Michelle, yours is, I think it's perfect. Give me 1 second. I thought the number. Yes. Yes, Michelle, yours is perfect. Elvis, yours is perfect. So did everybody get 1011 and then 011? 0111? All right, sorry. I thought I was gonna be able to handle this better. Didn't go as smooth as I expected it to be. Let's see, and all right, yes, B is 1011 and then 0111. Perfect, Hargo. Right, yeah. So you guys just remember, right? You separate it into nibbles, and then every nibble you translate it to binary. All right. Let's keep this up. All right, so via and chat, we have answers from you. Someone else use bitwise operations to turn off the 5th bit from the right of 0B11. So this is 1, 2, 3, 4, 5. So bitwise operations refers to bit shifting and bit masking. So I guess who wants to take? Oh, sorry, who wants to take this one? Or so if you want to try it, you can also send it over on a DM.
So could you do this with a and masking?
All right. And so how would you do this?
You would mask it. You would and mask it with 1110 1111.
110. Like this?
Yeah.
So 1, 2, 3, 4, 5. I guess it just just 4 zeros before this is the 5th one, but yeah. That's exactly right. Do you and then let me write it out in this just quickly so we can actually we can do it here. Right, so let's see, let's get the number. right, Zach, I guess you get to do it again. So, all right, and so, wait, spaces. So we want to unmask this. So what should I write here now? Just let me know. And we're the 5th from the right, so
The middle one.
1, 2, 3, 4. Oh no,
It's
this.
the middle one.
So this guy.
Yeah.
Ah,
Yeah.
okay, perfect. That's it. All right, Zach. So I'm sorry, guys. Everything's going not even close to as smoothly as All right, there we go. So Zach, just write out for us, please.
Yeah, so it'll be 1, 1, 1, 0, and the rest are ones.
All right, perfect. And so how does this work? Because then we're and masking, right? We're not or masking, we're and masking.
Right. So since we're and masking, adding a 1 doesn't change the original value because it's either.
Give them to me one by one.
Sure. Yeah. So it'll be 0, 1, 1, 0, 1, 1, 0, 0.
Right. And so if we compare this one to our original, we see they're exactly the same everywhere except here where we turned off the 5th bit. Right. That's bit and masking. Cool. Why do people tend to gravitate toward base 10 numbers while computers do better with base 2? I guess. Yes, I guess the most important part of this question is why computers do better with base 2.
I have a theory, and it's funny, but I think it makes sense. So
right.
because people are usually born with 10 fingers, and so naturally it would be more natural for people to count in 10. And computers, however, are built with switches, and the switch is only on or off. So there. So it naturally counts with zeros and ones, which is on, off and on.
Yep, exactly right. That's actually very, very right. It's particularly the part with the finger numbers. I'll show you in a second. Actually, let me show you right away. I don't know if you guys have heard about the Mayan number system, but so the Mayan number system was base 20, and it was base 20 because they had 10 fingers and then 10 fingers on their feet. So you could use that, and so you'd go from it's a little bit easier to do. Here you go. This one's actually better. All right, so this is the 0 shell. This was again, I'm telling you on Guatemala and everything, but Mayas were pretty cool. They had like the concept of 0 in their numbers. Like I think, I don't know, hundreds of years before everyone else. I don't quote me on this stuff, but they were something about them, and the 0 was pretty awesome. They got it before like everyone else. And here you go. Like these are the symbols, right? 1 is a 1 dot, a 2 is 2 dots. Then when you get to 5, and then you just keep adding those on top. And then when you in our number system, right, we go from 0 all the way to 9. And then if you move this number one spot to the left, then this gets multiplied by 10. And so instead of it being 9, it's 90. Similar to how an F and a 0 here, sorry, if this is hex, this is actually, 16, right? So, so this is 15, right? And then once you add one more, then this becomes 16, you move to the left. They just, instead of doing it from right to left, they did it up, down. And so this is, you see it here, right? Like 8 at the bottom and then 1 spot at the top. Think about this, like turning this part here, like on its side. And this is how we do it with base 10 numbers and base X and binary. But yeah, they use 20. Yeah, the whole, sorry, I'm going off a long tangent. But yeah, the whole point is they use 20 because we had 20 fingers. And then, but this whole base thing we talk about, right? Like, you know, the Mayans moved they had bases, right? They just moved it up instead of left. We move it left, but it's the same thing with binary, right? A 1 here means 1 because it's in the first spot. If it's the second spot, now it means 2. Then it means 4, 8, 6. Sorry, 16, 32, etc. All right. So nice one, Michelle. Someone else create an mask to preserve the last 3 right-hand digits of any 8-bit number. So I'll give you a new number. All right, so create an ant mask, someone, and preserve, what is it? The last 3 right-hand digits of any 8-bit number. So the ant mask you're gonna create is gonna work for everything, but let's just do it with this number as an example. Someone give me an ant mask to get the last 3 numbers.
0, 0, 0, 0, 0, 1, 1, 1.
Yep, pretty simple. And then since we're in this mood already, just call this out for me.
0, 0, 0, 0, 0.
Are you sure?
0.
You sure about this one?
The 5th one, yes.
All right.
The 6th one, 0.
You sure? There's a 1 over there.
1, 1.
All right. All right, and then you see, again, if we compare this to this one up here, these 3 last digits, they are, oops, oh, perfect. Yeah, these are all the same. All right, so Steve, you've also gone.
Hey, can you go back to that, the sample you showed, please? And this is an and just like the one on top, right?
Mm-hmm.
So why is it that on top, when we've got 0 and 1, it's a 0? Wait, can I see it? Hold on. Okay. So if 0 and 1 is a 0 and 0 and 0 is a 0, so the one on top could have also been the last 2 on the right that we're ending, could have been 0 and 0, and it still would have given us the same answer?
You mean, so if we did this?
Line 24,
Oh, no, wait.
if we put 0, 0 at the end.
Sorry, let me. So if we
Line 25 now, yeah. If that and that was 0 and 0, we'd have the same answer. I mean, looking at the one at the bottom that we just did on 34 and 35, 0, 0 equals 0, 0, 0 equals 0.
Mm-hmm.
So it could be either 1 or 0 there. Yeah.
Well, we're bit masking different things. So here we're trying to turn off the 5th bit. Right here we're trying to get the last 3 bits. So we're doing different things.
Okay.
But so with and masking, it will only return a 1 if they're both 1s. And so when you use a 1 on an and mask, it doesn't change the output from the original. Because it's either going to be 1, like if it's a 1, it'll be a 1. Sorry about the bird. And if it's a 0, it will be a 0. because they're not both 1.
Right, but we're not changing. If I change the last 2 to 0 and line 25, we're not changing the outcome. The outcome is 0.
Right, but if the input were different, if those were 1s, then you would get 0s.
You would get 0s.
Because
Yes.
so
yes,
then
but it's not.
But it's not. So like the 1 is universally gonna keep the input the same.
Oh, no matter what the number is.
Right. Yeah.
Okay.
But in this particular case, since the input was a 0, yes, it would stay a 0.
Well, if it was a 1, if on line 24 it was 1 1, and you had 1 1 at the bottom, it would be 1 1 on line 27. So.
Correct. Yeah.
Yeah. So it doesn't make sense to me.
Right.
Because you were saying that the last 2 on 24,
Wait a second.
0 0, right?
This is gonna get confusing. Let me.
Yeah, I am confused because the masking at the bottom did the exact opposite and came out with the same. I want to know why that did that, or if I missed something in the middle.
Yep, no worries. All right, so
because
yes.
the law of and is whether the only time it equals 1 is when it's 1 1 equals 1. So whether I put 0 or 1 there, it should be okay because it'll still give me 0 at the end, and my original number is not changed. I'm only changing the 5th position from the right.
All right, so
But you don't imagine you don't know what the original number is. That you only ever want to get the.
No, but the question is very clear from the right of, and that's the number.
all right, so let's see this in action. So you're saying, right, that in this particular case for this add masking, right? These two would give you the same answer, right? So like you're saying it was like SAC and masked it like this, and what you're saying is that
yeah, I'm saying, can it be that way? Because as long as 1 and 1 is not there, it will not be 1.
All right, so that's like Zach said, this is true for this very specific case where these 2 last items are 0, right? Like if you want to take it that far, then this then we can change to this one as well, right? And then because it's a 0, then it's going to go back to 0, right? But that's not quite what the sorry, 1 second. So
and the one I'm questioning is not the last one we did. The one that I'm questioning is the first one we did that had the specific number that we needed to change the 5th from the right.
Right. So what this is asking you to do is right, use bitwise operations to turn off the 5th bit from the right? And just the 5th bit.
Right.
So how do you turn bits off with by unmasking? Do you use a 0 or do you use a 1?
Depends what's.
No,
depends
it doesn't depend.
What the 5th bit is, right?
No, doesn't matter what the 5th bit is.
Okay.
So how would you turn it off?
Well, if the 5th bit was a 0, if the 5th bit was a 0, I wouldn't need to do anything.
Irregardless of what the 5th bit is. So let's say you don't know what the 5th bit is going to be, right? You're creating a general function that's going to take any binary number and it's going to turn the 5th bit off.
Okay.
How do you turn bits off? Do you use a 0 or do you use a 1?
In the case of and 0.
Yep. So
yeah. So, exactly. So back to my question: if you can do that, and the last 2 on 25 are off anyway, couldn't I use 0 0 there for that particular number, that particular case, and it would still be a correct answer?
Yes, it would still be a correct answer, but you're getting the process wrong. That's the only thing.
Okay.
Right? Because so like say this wasn't the particular number, right? Say like the particular number turned out to be this.
Yeah, and then of course it has to be 0, 0, 0. I mean, that makes perfect sense in my mind.
No. What I'm saying is if you unmask it like this, then, sorry, this is not where we want to change it, right? So right here, right? This is Michelle's question, right? So what you're saying is like, for this specific example, can't we do this and get the exact same answer?
No, my question is on top, not for that one. That one I get.
These two are the same.
No, but the one on top gave us a particular number to change the fifth from the right.
Mm-hmm.
So my question is, because we have that particular number, we don't change the last two numbers, whether it's a 1 or a 0 there on line 25. So are there two possible answers for that particular situation? Or
I think I know another answer for the situation.
Go ahead, Brian.
XOR. So if you shift, so like if you had a 1 and everything else was 0, and you shift the 1 however many places to the digit you want. So like if you start with just 00001 at the very end, and then you shift that 1 to the left to whatever position that you want. So like you want the 5th digit, so now shift the 1 to the 5th digit. And then from there, if you XOR that with whatever the 5th digit is, it's going to be, I think that might be the way to mask it. So like what happens if you mask that number? So it might be, because it's 0. So like 0, 0.
Let's see, I don't quite remember XOR. XOR
is basically if it's both. Yeah, so it's going to be 0 if it's both. But if it's just one or the other, then it's going to be 1.
Yes, that could also work.
For this number.
But then you might turn stuff off in here that you don't want to turn stuff off. So like say this 0 and 0, right? Since you're having zeros.
Yeah, I think that's what you mean.
No, see this one right here, right? Since actually no, yeah, you're totally right. That also works. So yeah, that's one way. But Michelle, so
yeah.
Back to your question. You're saying, isn't there like two ways to do this that would get you
the number
for this specific number?
To do the number 4 question.
To get this one, right? So if you're saying there's two ways to unmask this that would get you this answer?
I mean, I'm just by looking at the sample under it for the next question. Question 6.
So the thing is, there's a lot of different ways that you can unmask this to get the same answer because there's zeros, right?
Okay.
So let's see.
So tomorrow, if they ask the same question and I thought of as 1101100, it's still correct, right? Because you still get the 5th position to change from the right and nothing else changes.
So I mean, you're getting the right answer, but you're using the wrong process. So I don't think you get full points.
Okay.
Does it make sense why?
No.
Because if you use this unmask, then you're also turning off the first, second bits from the right and the third and the 5th bit from the right. And this one is asking you to turn off only the 5th bit. It's not
How
asking
am I
you to turn
turning it off when it's already off?
Doesn't matter, right? Like whatever this is, like you're still asking it to turn it off. Like this number right here, this unmask, it doesn't care what's above it. Whatever it's above it, it's going to set it to off, no matter what it is. If it's already off, then fine, it'll set it to off again.
Oh, I see. So
If
whatever
it's on-
the number at the bottom is the instruction.
Yes. This is just the input, and this is the function. And then what they're asking you is for like an n mask that will turn off the fifth digit. Like if you want to just like ignore the number from the question, right? So okay, just use bitwise operations to turn off the fifth digit from the right of a binary number.
Uh-huh.
Right?
Okay,
So,
okay. That makes more sense. I was confused because when we saw this sample, the second answer at the bottom, we were doing 0, 0, and then 0, and I was like, well, if I can do that, why can't I do that up there? I needed to know why. Thanks.
so yeah. So what this is doing is this is turning the last 3 bits on.
Right. Okay, yes.
So like an analogous to what you were talking about up there, right? If we did this, right, since this one's already off, if we did the 0, right, and only use these 2 ones, then you would still get the same answer, right, because this is already 0.
Uh-huh.
Right, like you could think about it that way, and then like, all right, okay, fine, yes, technically I'm still getting the right answer, but you would have to know like very specifically, like when you're writing a program, right, like you couldn't pass in any number, right, because right here you're only turning off turning on the first 2 bits, right? So even though this is getting you the right answer, like if you try to use this for some other number to turn on the last 3 bits, it's not gonna happen. Right?
So when we're talking about the number is irrelevant. And turning off and on, what we really need to think about is the
mask.
The number that we're gonna put beside the and.
Yeah.
The mask.
And so that's a beautiful thing, right? Like if you have this mask, you don't care what the rest of the numbers are. Like anything that gets passed in, you don't care at all what it is, because this guarantees that whatever that is, you're gonna get a copy of only those 3 last numbers, and then everything else is gonna be set to 0.
Okay, I understand now. Thanks.
Right? Yep. And what this is doing, right, is like it's guaranteeing you're gonna get a copy of everything else except the 5th digit, and that 5th digit you're gonna turn off.
All right. Okay.
All right. Okay. So next one, somebody describe how RAM is better than registers and vice versa. How they're better and worse. What are the benefits and disadvantages? I've got Brian and Elvis. You guys can still go.
Yeah, so I guess RAM. So the way RAM could be better than registers is that there's more space. So you can just, I mean, that's where you can store programs. You can store large amounts of data. Registers are, so that's the advantage of a RAM. So registers, the advantage would be they're closer to the CPU. They allow you to, they're close to the CPU, and they are basically just used for navigating through programs in RAM, I guess.
Yep.
Not very clear, but I think that's kind of
maybe speed, in other words.
Yeah. So registers are good for speed. RAM is good for space.
Better. Where's that? I know I copied that somewhere. Let me just get this for you. Oh, here we go. If you can draw this out or show them this, this is the answer you need, right? Registers are closer to the CPU, so they have greater speed, but they have less space. Memory is further from the CPU, so it has more space than the registers, but it's slower because it's physically farther away from the CPU.
Gotcha.
All right. And then I guess we saved this for last. Where's this last question? All right. You want to take a guess at this one, Elvis? If you know, otherwise I'll have to answer this one for you guys.
Yeah, I was about to ask if we did the jump command, but
No, we did not.
okay. So call's gonna execute the program, whereas jump maybe is just going to move you to a different place in memory and let you continue from there. I don't know. I'm not sure.
That's actually, yeah, exactly right. Do let them know if they ask you this question, like go ahead, try and give the answer so you don't sound like, oh, I'm trying to get off the hook. But do let them know that we didn't see this in the guided project. But so you actually have no experience, but the quick answer is yes, jump just move you somewhere else and moves the program counter somewhere else and drops it off. Call has a return address stored to you once you're done. So call is also paired with a ret return function, and it'll return back to wherever you left off.
Actually, you can see it if you go to the where's that? The examples, the code to run for call. If you look at it there, you can actually see that it does show you that call pushes current instruction pointer on the stack, and then you do a jump to the location, and then you do a ret to return back to where you were. What in the world? Why are you on my repo?
One, to show you that you haven't invited me as a collaborator because it doesn't show up in my in my search results. Two, so we can see what you're talking about. And examples, you said?
Examples. Yeah.
Which one?
Call LS8, because that's how we're gonna test the call. I finished MVP yesterday. That's why I know this. And when I think about how to solve the stuff that we need to solve, I always look at what it's supposed to run first, so I know what I need. So for call, I know I'll need to use LD. It'll use LDI. It'll use. Where are you going, Luisan?
Going to the spec sheet because it's
okay.
It's not that easy to read there.
Because you'll see it says call LDI, and then there's a. Is there not a jump there?
Right. You see jump in call.ls8. There's no jump instruction. Yeah.
Oh yeah, sorry.
But check this out. Either way, the programs don't give you that much info. They just give you the instruction and the arguments. But here's jump, right?
Yeah.
Jump to the stored address in the given register. Set the PC to the address stored in the given register, and that's all you do. Let's see what the expected for call is. Right. The address of the instruction directly after call is pushed onto the stack. Oh, sorry guys. People are making noise. Seems like it's a fight or something. Check it out. So okay, sorry. Setting the PC counter to the instruction right after call. Right, here it is. So directly after call is pushed onto the stack. And then the PC is set to the address stored in the given register. We jump to a location in RAM, and then the PC can move forward and back to a location. It doesn't really matter where it goes. Like it could jump back, it could jump forward, it could do both. But yes, we're storing the address, whereas in jump, we're not. Yeah, we're just jumping to the stored address in the given register, and that's it, not saving anything.
Yeah, sorry, that's where I saw it. Oh gosh, everything's getting crossed in my mind.
All right. So these are the sample questions. I know it's saying sample. I'm pretty sure these are going to be the questions. Yeah, so don't worry about it.
Those are the questions from last week.
Oh yeah, exactly.
I just looked through our feed and yeah, when they gave us our questions and the person that was supposed to interview us, those were the questions for the other group.
Cool. All right. So all right. Anything else you guys want to look over? I know some of you weren't that clear with bit shifting and bit masking from the little poll we did at the beginning, but would you guys like to see some bit shifting before we leave, or are you guys good? All right. So let me show you an inventory, show you specifically how it's used. All right, here we go. So instruction layout, right? Meaning of the bytes in the first byte of each instruction. So let's see, let's get these side by side. Perfect, even better. All right. There, 1 second. There you go. So AA is the number of operands for this code, right? So what is the number of operands for LDI? Anybody? Yes, SAC, that's right too. What's again, after that is B, right? So after these AA, it's a 0, 1. Oh. Is this or is this not an LAU operation? Yeah, so you're right, Steve, it's not. And this is what it's telling us, right? And then C, does this instruction set the PC? Instructions that set the PC are jump, call, ret, right? Like those kinds of functions. Let's see. So this is C, right? So that's the 4th digit. Let's have a look. So C LDI, for example, right? Look at the 4th digit, it's a 0, right? So it does not set the PC. How about jump? So have a look at jump. So 1, 2, 3, 4. Oh, check this out. It is a 1, so it does set the PC, right? Simple. Right, and then instruction identifier DDDD. So we it's just an extra number because in the end what we're reading is the whole instruction thing. So let's see if there's an easy way to print this out. So with bit shifting, right? Let's get LDI. I think it's just not going to be easy to see. Okay, then we'll do it. We'll do it manually since we can't print it out easily. All right, so we have our LDI here, and let's copy this over. All right, so say our LDI, we'll store it in our variable instruction. Right, and so when bit shifting becomes useful is, so say we want to get AA, right? We want to get this number. When we bit shift, right? If we say we bit shift right by 2, what we're doing is adding 2 zeros here on the left and removing 2 zeros here on the right, right? So this number here now turns into this number right here, right? And so notice how we're starting to get rid of the digits here and starting to push these digits to the back. If we keep doing this, right, if we do it by 4 and then we do it by 6, then what happen is, right, so we're going to get rid of 1, 2, 3, 4, 5, 6. And check this out. Now all we have all the way to the right is AA. Right, like this is where we left off. We got rid of all of these, and now we have just these guys. So 1, 2, 3, 4, 5, 6. And now we can simply read number of operands for this code. We can read the entire number, and we can know this is LDI. LDI has we know LDI has 2 operands, and so that's useful for us when we're running here this current index, right? Let's see. Let's do, instead of LDI, let's do print. So print set to this. Again, we'll bit shift print by 6. So we got a print here, and so we got a lot of things, but all we want to get is AA, right? We want to get all these first 2 numbers. So if we bit shift by 6, we're going to get rid of 1, 2, 3, 4, 5, 6 digits, right? And then we'll add zeros, just zeros to the left, all right? Because if we added ones, then we'd get a crazy number, and then that's not what we want. 1, 2, 3, 4, 5, 6. Yeah, that looks right. And so now we know what number is this. This is what. So this is the number 2, right? And this is the number of operands we have for load. This is print. Print, as you can see, only has 1 argument, right? And this is what you get. So one quick example of how this is useful is, instead of doing current index plus 2 and every one and checking that out and hard coding into every single one of our switch cases, we can do, so in our default, I'm gonna get a bit of the syntax wrong, but just bear with me for a moment. So, all right, so we're getting, let's say we get the command print, right? We're gonna get the command print, and so we run through print. We'll ignore this current index, and instead of setting that, we can set that dynamically by saying num of operands is set to our command, right? Our command is what we're reading from here. We're getting this command right here, right? This is a switch case. So this command is like a binary number. And then we can bit shift this by 6. And now we know that we're going to be left with just these last 2 numbers, right? And so now what we can do is then do current index plus equals num of operands. And then just that cleans up your code. That'll get rid of every current index. Notice that we have to do number of operands plus 1, right? Because if we're doing here and we just added 2, then we'd end up here, right? If we're here and we only number of operands is 1, if we only add 1, we'd end up here, and that's not what we want, right? Like, we're not at the instruction. So we do have to include this plus 1, but this is one way bit shifting useful. The next way we can use bit shifting, right? Like, okay, so we got A, B, and C, right? If we want to get D, D is pretty easy. How will we get D? And this doesn't use bit shifting. So how will we get these 4 Ds? Am I right? Like, I have this huge number. I have this, right? This is like, what, like 130. And I want to have access. I want to know what these 4 numbers are. Like, what these 4 digits, what do they add up to? So how can I get rid of this so that I don't take these 4 numbers into consideration? Say that again, Steve.
And masking.
Yep. How would you do that? How would you write it out?
0 0 0 0 1 1 1 1.
Yep, exactly right. And so what you're left with is just this last phrase. So 0 0 0 0 1, and then this is ones. We'll just copy over what we have from up top, and that's 0 1 1 1. And there you go. Now you have, so now this number has been transformed. This entire instruction has been transformed into only the instruction identifier, and you can use that for whatever you want. Now the trick for getting B and C is you just gotta know where they are and mask them, so you can know how much to bit shift and then mask. So let's get rid of this. So let's say we want to get, let's get rid of this too. We want to get B from this instruction. So B is, what is this here? The 6th digit. So this is not right anymore. So we want to get this B number right here, right? So we want to get rid of 1, 2, 3, 4, 5 numbers. So we bit shift by 5. Then we add 1, 2, 3, 4, 5 numbers here. And now that we have this instruction, we can unmask this. We know this is the last. Again, let's actually. So this is it. Right, this turns to, we get rid of 1, 2, 3, 4, 5, separate those, and then we add 5 more, 1, 2, 3, 4, 5 to that 1, 0, and then that's 0. So this is the number we want. So since we only get one number, this is pretty simple, right? All we have to do is unmask for the last one. So 1, 2, 3, 4, 5, 6, 7, unmask by 1, and there we go. If this were a 1, we'd get a. If this were a 1, we'd get a 1. If this were a 0, we get a 0. Simple. Same thing for C. We just bit shift one number fewer. So we want to get, let's do print because print looks a little bit more interesting. Right. So we want to get to C. C is A, B, C. So what do? We bit shift by 4. Right, so we go 1, 2, 3, 4. This is the number we want, so we'll separate it. Then we add 1, 2, 3, 4 zeros. And so we have 8 digits now. This is 7 right here, and this is 8. And then we take this number and we unmask it. And then now we're guaranteed that all of these are zeros. So, we get rid of this 1 right here, for example. I guess I'm missing one. And then here we go, and it's a 0, right? So that's bit shifting and bit masking. Any questions? All right. Any one last thing before you guys head off to lunch? I mean, I'm feeling a little bit bad about keeping you guys in here, but if you guys want to answer some more questions, we can still hang out. It's up to you guys. Any other questions you guys want to check out? All right, cool. Then head out for lunch. I'll start getting this recording uploaded, and you can check it out if you need it. But yeah, just again, reach out if you have any questions. Don't suffer in pain don't suffer in silence for too long. And yeah, I'll see you. If I don't see you in stand-up today, good luck in the sprint tomorrow. I'll be around for questions as well. But yeah, see you guys after lunch.